Hello everybody. In this video, we're going to practice counting. This is problem number 1. A university has 3 colleges: Science, Engineering, and Arts. Science College has 19 staff, Engineering has 10 staff, and Arts has 17 staff. And male-female distribution of those staff is given in the chart. Once you make your chart, it's easy to answer any kind of questions. What is the total number of ways these 3 deans can be chosen? We are picking 3 deans, one from each college. So we are picking 1 from 19, so 19 choose 1, times 10 choose 1, times 17 choose 1. And 19 choose 1 is 19, and 10 choose 1 is 10, and 17 choose 1 equals to 17. So 19 times 10 times 17 is the total number of the ways we can pick 3 deans. Part B is asking how many ways can 3 deans be chosen, so at least one of them is female. So we can approach this question from the complement. Total number of ways, total ways, minus no female, picking no female, will give us at least one female is picked. So total number of the ways we already calculated from part A, which is 3,230. Here, total number 3,230 minus, we are going to pick up no female. So picking no female from the Science College means 12 choose 1, times picking no female from here means 7 choose 1, because we're picking only male here. Likewise, 7 choose 1 will give us the answer. So this is going to be answer. Problem number 2. Our indiscrete mathematics course has 28 students from College of Arts, 19 students from the College of Engineering, and 35 students from the College of Science. And male-female distribution is given in the chart. Again, you start by making your chart. How many ways can we choose a single class representative? We are picking single class representative from the total math course, because that total students are making one course total students. So it is 82. Answer is 82. Or you can think this like that. 28 choose 1 plus 19 choose 1 plus 35 choose 1 equal to 28 plus 19 plus 35. Or you can think it like this. 3 coordinates combined. For the first coordinate, we have 28 options. And for the second coordinate, we need 19 options. And we have 35 options here to pick up one class representative. Part B, how many ways can we choose 3 reps, one from each of the 3 colleges? So this time, 28 choose 1 times 19 choose 1 times 35 choose 1. We are picking one representative from each college. And this is the multiplication rule. So we have 28 times 19 times 35 different ways of picking class representative. Part C is how many ways can we choose 3 representative, one from each of the 3 colleges, so exactly one is female. This time we're going to combine 3 different situations. We want to ensure, and picking male from engineering is 11 choose 1. Picking male from science is 15 choose 1. Picking male from arts is 10 choose 1. Picking female from engineering is 8 choose 1. And picking male from science is 15 choose 1. Picking male from arts is 10 choose 1. Picking male from engineering is 11 choose 1. And picking female from the Science College is 20 choose 1. So we ensure we picked female from each college alternatingly and males from the other colleges. And combination of this will be the number of the ways we can pick up 3 representative and ensure exactly one is female. So whatever this number is the answer. 18 choose 1 is 18, 11 choose 1 is 11, 15 choose 1 is 15. So multiplication of these 3 numbers plus multiplication of these 3 numbers and multiplication of these 3 numbers. Problem number 3. A ternary string is a string made up of zeros, ones and twos. How many ternary strings of length 4 are there? So we have 4 coordinate here, and for the first coordinate we have 0, 1 and 2, 3 options. Likewise we have 3 options in each coordinate because we have no restriction. So this is going to be 3 to the 4th. Problem number 4. 4-letter words are formed using the letters A, B, C, D, E, F, G. How many such words are possible for each of the following conditions? A. No condition is imposed. This is like ternary string question. We have 4 coordinates and each coordinate has no restriction. So for each coordinate we have 7 options. We have 7 letters here. So it's going to be 7 to the 4th. Part B is asking no letter can be repeated. Since no letter is repeated, for the first coordinate we have 7 options. For the second coordinate we have 6 options because we cannot repeat. Likewise 5 and 4. So this is going to be the answer. Or you can consider this as the permutation of 7 fours, 7 to 4 permutation. And permutation by definition is n factorial over n minus r, the quantitative factorial. So it is like 7 factorial over 7 minus 4, which is 3 factorial. You can use either. Part C is asking each word must begin with letter A. So again we have coordinate of 4 and each word has to start with A. So A is here and we were not given any other restriction, and we have 7 options here, 7 options here, 7 options here, and we have only 1 option here. So 1 times 7 to the 3rd. The letter C must be at the end. This is the same situation as C. We were given restriction that C has to be here. However, we were not given restriction here. It is going to be 7 to the 3rd. The second letter must be a vowel. We have coordinates of 4 and second letter is the vowel, and we have only 2 options here, either A or E. For the situation A, we have 1 option here, which is A, and we have 7 options here, 7 options here, 7 options here. For E, we have second coordinate is E, and we have 7 options here, 7 options here, 7 options here. And if we combine this, it's going to be the number of ways. So it's going to be 7 to the 3rd plus 7 to the 3rd. Or you can condense it and write 2 times 7 to the 3rd. Either way, it is the answer. Problem number 5. At a restaurant, there are 5 kinds of pasta and 2 types of sauce. How many different ways can a customer order 1 kind of pasta and 1 type of sauce? This is simple multiplication rules. This is simple multiplication rule. This is going to be 5 times 2, which is 10. It is important to understand this multiplication rule, so I would like to illustrate, because more complicated questions in the multiplication rule is based on this theory. Let's say we have 5 different kinds of pasta. And to distinct, I would like to give different colors for each. And let's say we have 2 different kinds of sauce. and let's distinct it. So for the red pasta, we can pick up this, and for the red pasta we can pick up this sauce. So red pasta can create two different kind of orders, and white pasta you can pick up blue sauce and you can pick up orange sauce. So you can order two different kinds with this pasta. Likewise, so it's going to be 5 times 2, because you're going to add those numbers, which is going to be 10, which is 5 times 2 is 10. But if the numbers are big, you're not going to be able to add or make some chart like this. So multiplication rule is one kind times the second kind. Problem number 6. Michelle chooses one square and one circular disc from the squares and discs shown below. How many different ways can Michelle choose one square and one disc? This is similar question as we did on problem number 5. We have 4 options for squares times we have 2 options for discs, which is 4 times 2 is 8. Problem number 7. A girl owns 8 pairs of pants, 8 shirts, 8 ties and 5 jackets. How many different outfits can the girl wear to school if each outfit must consist of one of each item? This is again multiplication rule, and we have to use one of each, and we have to multiply 8 times 8 times 8 times 5. Problem number 8. James owns 8 different mathematics books and 6 different computer science books, and wish to fill 5 positions on a shelf if the first 2 positions are to be occupied by math books and last 3 by the computer science books. In how many ways can this be done? Let's illustrate this question. So we have 5 different sections of a shelf, and we would like first 2 filled by mathematics books and last 3 with computer science books. And to be able to distinct, I would like to give some letters. For the first 2 sections, we are placing mathematics books, and we have 8 math books, and we are picking only 2 options here. So 8 choose 2 is the place for math books, but A can be the first or B can be the first. So we have 2 factorial options times 8 choose 2, and times, we're gonna use the same logic here. For computer books, we have 6 computer books, 6 choose 3. However, we don't know which computer book will be the first, second or third. We have to alternate that. So it's going to be 3 factorial because we have 3 sections here. C can be the first, D can be the first, or E can be the first. Similarly, you can alternate. So this is going to be the answer. Problem number 9. A company has 1,125 employees. Each employee is to be given an ID number that consists of 1 letter followed by 1 digit. So we have 2 coordinates, 1 letter and 1 digit. How many different ID numbers are possible? For letters, we are, I think, thinking in English alphabet, 26 letters. And we have 0 to 9, we have 10 options here. So 10 options here, the digits are from 0 to 9 all over the world. And English alphabet has 26 letters. So 26 times 10 is 260 options. And is it possible to give each employee a different ID number? No, because we have 1000 something employees, but the number we can generate is maximum 260. After 260, it has to be repeating. So no. Problem number 10. A fair 6-sided die is rolled 5 times and the resulting sequence of 5 numbers is recorded. How many different sequences are possible? So we have coordinates of 5 that we need to fill. And for the first coordinate, we have 6 options from 1 through 6. Likewise, we have 6 options in each coordinate. So it's going to be 6 to the 5. How many different sequences consist entirely of even numbers? So this time we still have 5 coordinates, but we would like even numbers here, which is 2, 4, and 6. We have 3 options for each coordinate, so it's going to be 3 to the 5th. How many different sequences are possible if the first, third, and the fourth numbers must be the same? So let's work on our 5 coordinate system. We would like our first, third, and fourth to be the same. So let those coordinates be number 1. And here we have 6 other options, 6 other options. However, that could be number 2, number 3, number 4. So we have 6 different options for those defined spots. It could be number 1, it could be number 2, 3, 4, 5, 6. And the rest, this part is free. So it's going to be 6 times 1 times 6 times 1 times 1 times 6, or 6 to the 3rd. But it is better to write 6 times 1 times 6 times 1 times 1 times 6 to understand what each coordinate is taking. Problem number 11. A standard Missouri state Problem number 11. A standard Missouri state license plate consists of a sequence of 2 letters, 1 digit, 1 letter, and 1 digit. How many such license plates can be made? So we have 2 letters here. Let's call it LL. We have 1 digit, 1 letter, and 1 digit. This is certainly in American alphabet, because Missouri state. 26 letters options we have, 26 letter options we have. So digits from 1 to 10, we have 10 options here, 26 letters and 10 options. So that is the answer. But in the previous question, you could object about the number of the alphabet. Part B is asking, standard New York license plate consists of a sequence of 3 letters followed by 3 digits. How many such license plates can be made? So we have 3 letters followed by 3 digits. Each letter coordinate takes 26 options and each digit takes 10 options. So this is going to be the answer. So this is the total number of license plate we can generate. Problem number 12. A bit is a 0 or a 1. A bit string of length 7 is a sequence of 7 digits, all of which are either 0 or 1. How many bit strings of length 7 are there? This is 7 coordinate that we need to work on. 1, 2, 3, 4, 5, 6, 7. And we know that each coordinate takes either 0 or 1. We have no restriction here. So we have 2 options for each coordinate, which is 2 to the 7th. Part B, how many bit strings of length 7 or less are there? So this time we're going to use our template of 7 coordinates again. So for this we can generate 2 to the 7th for this type of template. and one last, which is 6 coordinate, we can generate 2 to the 6th, 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st, and 2 to the 0th, which is empty. And if we combine this, that's going to be the answer. So here we have no restriction, and maximum we have 7 coordinates or less, which is 6 coordinate, 5 coordinates through 0. So 2 to the 7 plus 2 to the 6 plus 2 to the 5. This is the answer. Problem number 13. A true-false test contains 17 questions. In how many different ways can the 17 question test be answered? You can think this question like bit strings, which is 0, 1, or true, false. That is binary system. We have 17 questions, which is the coordinates of 17 of spots, and each spots take 2 options only. So it's going to be 2 to the 17th different ways. Problem number 14. In a cohort of 30 graduating students, there are 3 different prizes to be awarded. If no student can receive more than 1 prize, in how many different ways could the prizes be awarded? This is 30 permutation 3, because out of 30 students we are awarding 3 of them, and the order is important because no student can receive more than 1 prize. And 30 permutation 3 by definition is 30 factorial over 30 minus 3 factorial. Or you can think it like that. You have 3 awards to be given, and the first coordinate can be one of those 30 students, and the second coordinate can be only one of those 29 because we cannot reward the same student, and this is going to be 28. And if you multiply those each coordinates, that's going to be the answer. You can either write in this form or in this form, or execute the number. Problem number 15. In how many ways can 4 different novels, 2 different mathematics books, and 1 biology book can be arranged on a shelf if the books can be arranged in any order? We have no restrictions, and all of the book kinds are thought like one kind. So 4 plus 2 plus 7, we have 7 different kind of books. So it's going to be 7 factorial, which is the permutation of 7. Because we cannot use same book in 2 different positions, which is physically impossible. So this is understood, order is important. Part B, the mathematics books must be together and the novels must be together. So we have 4 different novels that we can rearrange them in 4 factorial different ways, and math books 2 different ways. And biology book plus the bundle of math books and novels together makes 3 different kind, times 3 factorial. You can think it like this. You have 4 different novels, and you have 2 different math books, and you have 1 biology book. So this bundle itself can be arranged in 4 factorial way, and this bundle can be rearranged in 2 factorial way. Either this A box in front or B box is in front. And the last spot here is biology book, and biology book can be either in this position, in here, or at the beginning. So that separators can be the position of biology book. So biology book plus those bundles together make 3 books. 1, 2, 3. So that's 3 factorial. The novels must be together, but other books can be arranged in any order. So novels are together, which is 4 factorial way, and other books can be by itself, So 2 math books, 1 biology book, plus that bundle is altogether 4. So 4 factorial times 4 factorial. Again, same logic. It can be like this bundle can be first, or this bundle can be first, or biology book can be in the separators. So in this type of questions, the last spot plus each bundle will be counted. So that is going to be 4 factorial times 4 factorial. Problem number 16. How many 3-letter words can be made from 8 letters if repetition of letters are allowed? So if we allow repetition, for the first spot we have 8 different letters, likewise 8 different letters, so 8 to the third. And for part B, repetition is not allowed, so 8 times 7 times 6. Problem number 17. How many different 10-letter permutations can be formed from 8 identical H's and 2 identical T's? So we have 8 different identical H's and 2 identical T's. So you can consider that like 2 letters, because it doesn't matter which H I pick and which T I pick. It doesn't matter. I have 2 letter options here out of 10 letters. So it's going to be 10 choose 2, which is 45. Problem number 18. In how many ways can 5 books be chosen from a group of 9? This is directed definition of combination. 9 choose 5. And 9 choose 5 by definition is 9 factorial over 5 factorial times 9 minus 5, the quantity factorial. Problem number 19. A pizza parlor offers a choice of 16 different toppings. How many 6 toppings pizza are possible? So we have 16 different toppings, and we would like how many 6 different group we can combine. It is 16 choose 6, and it is going to be this. Problem number 20. A school dance committee is to consist of 2 freshmen, 3 sophomores. Let's write as we are reading. 2 freshmen, 3 sophomores, 4 juniors, and 5 seniors. If 6 freshmen, 7 sophomores, 9 juniors, and 7 seniors are eligible to be on the committee, in how many ways can the committee be chosen? So we were given that 6 freshmen is eligible to be on the committee, so 6 choose 2 times 7 choose 3 times 9 choose 4 times 7 choose 5. So let's make sure the numbers are 6 freshmen, 7 sophomores, 9 juniors, and 7 seniors are eligible. So out of them we can pick 2, 3, 4, and 5. So this is the answer. Problem number 21. How many ways can 4 CDs be chosen from a case of 10 CDs? 10 choose 4. Problem number 22. A standard deck of cards consists of 4 suits: clubs, diamonds, hearts, and spades, with each suit containing 13 cards, ace through king, for a total of 52 cards in all. How many 7-card hands will consist of exactly 2 hearts and 3 clubs? So we're picking 2 hearts out of 13 cards, because we have 13 hearts, 13 spades, 13 diamonds, and 13 clubs. And out of those 13 hearts, we are picking 2. So 13 choose 2 times and 3 clubs. So 13 choose 3. Another from 13 clubs, we are picking 3 of them. And 2 plus 3 is 5, plus 2 is 7. We have to make total 7 card hand. So we have 26 none. So we are picking here hearts, we are picking here clubs, and this is the none card. So that is the answer. Problem number 23. A company received a shipment of 37 printers, including 6 that are defective. 2 of these printers are selected to be used in the copy room. How many selections can be made? We were not given any restriction here, so out of 37, we need to pick 2 of them. 37 choose 2 is the answer. How many of these selections will contain no defective printer? So we have total 37 printers. We need to subtract the defective ones because that's our restriction. We don't want it. And choose 2. So it's going to be 31 choose 2. Problem number 24. A standard deck of cards consists of 4 suits, with each suit containing 13 cards, for a total of 52 cards in all. How many 7 card hand will consist of exactly 3 kings and 2 queens? So we want exactly 3 kings, which is, we have 4 kings in standard deck. So 4 choose 3. First we pick kings, times, then we pick the queens, which is 4 choose 2. We have 4 queens and 4 kings, and that's the none card. This none card, and we have to make sure there are no kings and queens inside as well. So 52 minus 8, which is 44. So 44 choose 3 plus 2 is 5 plus 2, so 7 card hand. So this is the answer. Thank you for watching.